This is Robert Capella from University of Wyoming, and he'll be talking about the high-resolution rapid refresh model-based analysis of snow squall characteristics.
Good afternoon, everyone. I'm Bob Capella. Thank you, Rob, and thank you, everyone, for hosting us. I'm a graduate student at the University of Wyoming. Today we're going to talk about a HER-based analysis of the characteristics of snow squalls, and specifically the first part of this research, which is a climatology of the snow squall parameter, which we saw the equation of earlier, and its component terms in the high plains and Mountain West. Collaborators are listed from the University of Wyoming and the Cheyenne office as well. So a brief outline. We're going to be talking briefly about the background and motivation, which was covered in the previous presentation, the objectives and the methods for this particular portion of the research, the climatology results, and the summary, and most excitingly, the future work to be done. So a little bit of background. This is from the WDTD walk module. Snow squalls are mesoscale, shallow convective systems that produce gusty winds and blowing snow. They're also characterized by a rapid onset and low visibility that, in conjunction with rapid freezes at the road surface, are extremely dangerous for drivers, especially those traveling at a high rate of speed along interstates. So again, this is the issuance criteria that was mentioned previously. I just wanted to note that a lot of times in the high plains and Mountain West, some of these shallow systems will fall beneath the radar beam, so they need to be confirmed through other methods, whether that's DOT reports, webcams, or road network observations. The two conditions we talked about earlier, namely the quarter-mile visibility in snow and the sub-freezing temperatures, the visibility brought about by either falling snow or blowing snow, creates these dangerous conditions. It also should be noted that a forecaster has to use their judgment on whether or not the societal impacts warrant the warning or the SPS. And that could be, time of day, traffic patterns, etc. So aside from the motivation that was talked about in the last presentation, 24 snow squall warnings were issued last year between the Riverton and Cheyenne offices. And because this type of alert is new, we want to understand snow squalls better for the warning forecaster, and whether or not the operational high-res models can capture these systems, and especially capture these systems in areas of complex terrain, which we're especially worried about. So the objectives of this particular portion of the research is to characterize the snow squall frequency and distribution via the snow squall parameter as a first step in the HER model. This work is going to support the larger work that Rob alluded to earlier. The two project-related, C-STAR project-related snow squall objectives are to develop a HER-based snow squall product, examine the accuracy of the HER in prediction of snow squalls and blowing snow, and then to use the HER for real-time dissemination of forecasts. So the method for this portion of the research, we analyzed the 3-kilometer HER output, which we hope would resolve terrain features, and it analyzed it for the snow squall parameter by Banakis et al. In his 2014 paper, and its component terms, and see its spatial and temporal distribution in the target domain, which I'll show shortly. We analyzed 3 cool seasons of available HER data. We defined the cool season as November through April, and we used the 2016-17 through 2018-19 cool seasons. We analyzed the 3 hourly data, so 0Z, 3Z forecast, 0-hour forecasts, and the 3D outputs were analyzed. So looking at this equation, and I heard some angst for equations just a minute ago, but this one's not too bad. The snow squall parameter, which is calibrated to 1.0 over 36 cases that were identified in the Northeast, this is the snow squall parameter. So it's given by term 1, which is the surface to 2-kilometer mean relative humidity in the column. It's set to 0 if the column relative humidity is less than 60%. And it's also set to 0 if it's negative, so again, less than 60%. It's given by stability, so the threshold for stability is given by the theta E value at the 2-kilometer layer minus the theta E value at the surface. If that value is less than 4 Kelvin, or excuse me, if that value is less than 4 Kelvin, then the atmosphere is too stable for snow squalls to form via this parameter. So that encompasses both unstable, neutral, and slightly stable conditions, also set to 0 if negative. And then finally, the 0 to 2 kilometer mean wind speed. This isn't set to 0 at a threshold of 9. It's actually set to 1 at a threshold of 9 meters per second, or about 17.5 knots. So I mentioned I wanted to show an example of the domain that we used, and I'll show more detailed plots. But this is just a quick look at the domain from western Utah to eastern Nebraska and southern Colorado to just south of the Canadian border. For some of the terrain effects, I wanted to show the upper level mean winds during these periods. Again, this is November through April for the 3 seasons. And we just keep in mind that there's a west-northwesterly wind for the majority, almost all of the domain, between 25 and 35 knots. So now I wanted to talk about the seasonal and diurnal trends. So for these plots that I'll show for each of the terms and then the snow squall parameter, the left plot is going to be the seasonal trend, so that's November through April by month, and the right is the diurnal trend starting at 0Z going to 21Z. The boxes are the interquartile ranges, the red are the medians, and the whiskers stretch out to 1.5 times the interquartile range. So this first plot is for relative humidity across the domain. We see that there's a maximum in frequency of mean 0 to 2 kilometer relative humidity in greater than 60%. So this is a threshold exceedance frequency of 60%. And we see a maximum in the wintertime months with the maximum in February. More expectedly, and maybe interestingly, is the diurnal curve. We had expected, a relative humidity maximum in the pre-dawn hours, and that's what we see with a maximum near 9Z. Moving on to stability. Again, this is the frequency of the 0 to 2 kilometer theta E difference of that 4 Kelvin threshold. So again, unstable, neutral, or slightly stable conditions that would set the snow squall parameter to above 1. And again, not many surprises here. We see increased frequencies of unstable conditions in the transition season, so late February, March, and April. And then we also see those same trends in the afternoon hours. So, not many unstable conditions in the pre-dawn and morning hours. Of note, the CAPE greater than 50 joules per kilogram, which was a threshold mentioned in the 2014 paper, follows the same trend. Again, no surprises there. Wind speed, it should be noted that this wind speed frequency, again, isn't set to 0 at the 9 meters per second threshold, which is illustrated here. It's set to 0 at 0 meters per second, but that rarely happens. And it doesn't really happen in the HER models, which Ethan will show shortly. So we see a maximum in the wintertime months in December, January, and February. And we also see a pretty tame diurnal trend with some slight increases in variability in the afternoon hours. So when we put it all together, we look for frequencies. Here is illustrated frequencies of the snow squall parameter greater than 0.6. Now I mentioned that the snow squall parameter is calibrated to 1. Banakis et al. Had identified 0.6 as the lower bound of the interquartile range of his 36 cases that he studied. And so this is used here for illustrative purposes for this and the following plots. But we see it follows the instability curve, or the diurnal and seasonal trends of instability, which kind of alludes to the idea that you're not going to have snow squalls without any instability present, which makes sense with how we understand snow squalls as they physically manifest. So now I wanted to get into the spatial distribution of snow squalls, and here it's the same plot. So this is the frequency of the mean 0 to 2 kilometer relative humidity greater than or equal to 60%. So we see local maximums in this plot along and upstream of, or on the upslope side of major ridge lines. So for example, the Bighorn Mountains in central Wyoming, or north central Wyoming, we see along that ridgeline and just on the upstream side a maximum. If you look farther west in the Absarokas, which is in northwest Wyoming, I have a laser here. the Absarokas in northwest Wyoming, we see that same maximum and then a minimum on the downstream side. Again, this just implies drying on the downstream side of mountains, so it makes physical sense. This is the same plot for stability, so the frequency of the 0 to 2 kilometer theta E difference being slightly unstable, neutral, or slightly stable. Here, the main takeaway is that, like we saw in the previous plot, there's a lot less frequency of occurrence of unstable conditions, which again alludes to the idea that if unstable conditions occur, then there's an opportunity for snow squalls via the snow squall parameter if the relative humidity and wind speed conditions are in play. And you'll notice that this is less than both the relative humidity plots and the wind speed plot, which I'll show next. There is some evidence of terrain effects in downstream of some of the major mountain ranges where we would expect that mechanical mixing could neutralize the atmosphere in the lowest 2 kilometers. And finally, I think this is the most interesting plot for this area, for the Intermountain West and High Plains. This is the frequency in the winter months of the 0 to 2 kilometer wind speed being above 9 meters per second, or about 18 knots. We see maximums upwards of 80% in some regions where the wind speed is almost always above this 18 knot threshold in the winter months, particularly along the I-80 corridor, stretching all the way into central Nebraska. From southern Wyoming, crossing the Laramie Valley, Cheyenne, and stretching into central and eastern Nebraska. There's also a noticeable minimum east of the Black Hills. This stretches all the way into eastern South Dakota. So one of the takeaways I want you to remember before I get to the next plot, which is the snow squall parameter, is that if instability occurs, that these terrain effects, which affect the relative humidity and wind speed distributions in this spatial domain, are going to govern the locality of where snow squalls are climatologically likely to occur per the snow squall parameter. And so again, this is the snow squall parameter of 0.6 of times that it's occurred over the time period. I wanted to note that the color bar is slightly different here. This, instead of 0 to 100%, this is 0 to 7%, just more infrequently that these three variables are co-located. But some interesting notes that the snow squall parameter is climatologically more frequent along the I-80 corridor, which has huge implications for road networks and the warning systems that we have for these road networks. But also those same truths hold as for relative humidity, where upstream and along ridge lines you see maximums of the snow squall parameter. Again, in the Bighorn Mountains, this is evident. There's also a maximum along the Black Hills, and it's a little faded here, low frequency of occurrence, but there's a maximum that stretches on the northern side of the Black Hills, so north of it's I-90, and also along this I-80 corridor that stretches into central Nebraska. So in summary, via the snow squall parameter, low-level instability seems to have the most limiting effect on snow squall development across the High Plains and Mountain West. Terrain influences are resolved within the 3-kilometer HRRR, which is what we were hoping to find. And those effects are observed in the threshold exceedance frequencies of relative humidity and wind speed. And then finally, the heavily trafficked corridor in southern Wyoming is a hotspot, a climatological hotspot. We knew this of high winds blowing snow and snow squalls, but it's nice to see it via the snow squall parameter in the study. So for future work, one of the immediate things we need to do is mask some of the below 1 degree Celsius wet bulb temperature occurrences of the snow squall parameter, because that is evaluated independently, lift is evaluated independently, and synoptic conditions are evaluated independently. So we need to think about how to include those in this climatology. Then we want to build a climatology of the hazard components of snow squalls in the HRRR, whether visibility falls below a quarter statute mile in certain areas more than others, etc. Evaluate the HRRR model's ability to predict snow squalls in complex terrain against observations. It's incredibly important to get this HRRR information and make sure that it's observed in real life. then disseminate the winter weather hazard forecast in the manner that was presented earlier, and then finally develop the higher resolution HER-like WRF simulation to explore more resolution dependencies of the snow squall parameter, the snow squall formation, and the HER model. These are just some references I used for this presentation. And with that, thank you, and I'll take any questions.
We've got time for some questions or comments.
So Western Nebraska, is kind of our area, so I'm interested, since we're in the domain, and maybe you may have said it, but I may have missed it, as far as real-time modeling and that sort of thing, availability on web pages or whatever, that maybe we can look at.
Sure. So one of the main goals is to disseminate this forecast to all customers, one of them being the people at the forecast desk. Although the snow squall parameter is available in AWIPS and D2D, but we look to improve that. But we also plan on disseminating these products via that kind of scrollable public web page that either a forecaster could use or maybe a DOT customer could use as well. We're in close collaboration with how best, and we would love to have you join the conversation of how best to make that either parameter, or if we develop a new version or a tweaked version of the parameter, how that can best be applied to the forecaster at the desk. In the long term, I really hope that we can involve the HER-E and use an ensemble approach to attack some of these problems, especially for the convective nature of snow squalls. That's a little bit down the road, but I think there's a lot of really great collaboration efforts to make sure that we're guided in the right direction, make sure the best product's on your desk.
Okay. Yeah, I've actually talked to Rob about, just staying at least on the fringe of the loop, just so we can make use of some of the great work you guys are doing.
Great, thank you.
Yes, this is now getting started, so I don't even think you have a domain for that, for the actual website, right?
I do not.
Yeah.
That's really, we're just getting started.
That's just getting started with that?
Yes, yes. This project is very fresh. Great.
Okay.
Thank you very much.